properties from the mantle to the critical zone. So I'm hoping that everybody's going to come here to see this. A lot of us are really curious to see what Scott's going to talk about. So for now, I'll let Kip introduce our speaker for today.
Okay, well, it's my really great pleasure to introduce one of our distinguished alums, Dr. Patrick Gathogo. I think, as far as I know, Patrick first became associated with the University of Utah through the work of Frank Brown, as many of you, perhaps not all of you, but was for a long time the dean of the college here, and worked extensively in East Africa on early hominid sites. And Patrick, with Frank, completed a BS, an MS, and a PhD from our department. He is one of the world's leading experts on the geology of the Turkana Basin. And he first started working there, I think, in 1996, under the invitation of Doctors Richard Meave and Louis Leakey, who many of you probably know of from the Leakey Foundation. After he graduated from our department, Patrick went to work as the head of the reservoir Petrology group at Schlumberger Oilfield Services. He is currently a research associate professor at Stony Brook University. He also is a research associate at the National Museum of Kenya, and he's an adjunct member of our faculty here. So we're really excited, Patrick, to have you here today, and he's going to talk to us about from the study of human origins to the exploration of petroleum, the petrology link. So, Patrick.
Thank you very much for the introduction. So I'm very happy to have this opportunity to present some of the things that I've been doing, and this is I hope it's going to be very informative and exciting to you as well. So I started here as a geology student, and I came here to study human evolution, the geological context of hominid fossils in East Africa. And then my advisor, who was Frank Brown, who was the dean at the college, he sent me to as an intern in the oil and gas industry. So I did a lot there, and then finally I came back to continue with a lot of things that we were planning to do concerning human evolution. So I'll be talking a lot about petrology. And to me, this became, I learned the value of petrology in geology from my advisor, Frank Brown. And the way he used to describe it to me, it's almost like petrology is like molecular biology equivalent for geology. You can look at very small microscopic things that will tell you much about the behavior of a rock. And that's what I'll be discussing and showing you the link, how petrology, you can be able to learn something from oil and gas and be able to use it for the study of human evolution. So this is an example of an SEM image that I took. Actually, I took it here at the University of Utah. And there you can see a lot of things there, organic material or bacteria associated with minerals. And it's a very, very predictable association between certain types of organic material and the minerals that you find there. And that is very helpful in the oil and gas industry because they're after hydrocarbons that come from organic material. And it's also very important for the study of a fossil because we are looking for skeletal material. So hopefully I'll be able to illustrate how that technology is transferable between the oil and gas and the human evolution. So I'll be talking about three aspects. First of all is mostly petrology, even though it's a very old science, but recently it's been making a lot of advancement in terms of understanding, particularly for oil and gas. And I'll also talk about various aspects that petrology is used, particularly for engineers. It has been used for engineers for a very long time, particularly in the construction industry. but also how I'm using it for paleontological or in relation to biology. And so I'll give a lot of examples concerning the application of petrology in the oil and gas industry, and then I'll shift to the human origins. And first of all, because sometimes when I talk, give presentation about petrology or what I do, I tend to almost turn into a preaching mode. So I always start with the acknowledgement so that I don't run over and I don't have time for acknowledgement. So I'd like to acknowledge the University of Utah. So I got a lot of funding, research funding, and also scholarship as an undergraduate at the University of Utah. And also the Leakey Foundation helped a lot with the funding for fieldwork that we did in East Africa. Even now, some of the projects that I'm doing are funded by the Leakey Foundation and the National Museums of Kenya, because that is the first place that I went and I got started as far as the human evolution is concerned. I went there as an intern, even before I started my university education. And that's where I met Richard Leakey, and he invited me to go to the field, and he then introduced me to Frank Brown, and then I got a scholarship to come here. And now most of the work that I do is with the Stony Brook University, because they have an association with the Turkana Basin Institute study. They do a lot of study on human evolution. And also the National Geographic has been funding a lot of work that I've been doing through the Leakeys. And Africa Oil has been providing a lot of data, seismic data, and a lot of data that we use for the study of the geology in the Turkana Basin. Because it happens that the same basin where the hominids come from, there are also gas reservoirs there. So, and this, I want to dedicate this talk to two people who have been very important as far as my career is concerned, and that is Professor Francis Brown. He was my advisor, and Richard Leakey. That's the person who introduced me to Frank Brown. And actually, I just came back from Africa together with Erica for a joint memorial service for both Frank Brown and Richard Leakey. They were like brothers. As you can see, they were almost the same age. They started working in the 60s in Ethiopia, and they worked together, moved to Kenya, and they did a lot of work together. So my dedication is to those two people. And so this is a picture from the 60s when they were working in the Omo Valley, and that's Frank Brown there. So he was part of the American team, and Richard Leakey was part of the Kenyan team. And after they were done, so this is where Ethiopia is, the Omo Valley. Richard Leakey decided to try and venture southwards into the Kenyan part of the basin to see whether they could also see outcrops that are fossiliferous. And the person that he chose to help me with that was Frank Brown. So a lot of geology for the Turkana Basin was really done by Frank Brown, and a lot of studies on human evolution was by the Leakeys. So, and just for context, so this is the size of the size of the Turkana Basin, the drainage basin of the Turkana. So I overlaid it on top of the map of the US, so that at least you can have a sense of how big it is. So the top is the border of Nevada, and it goes all the way up to like near Los Angeles. So a lot of sediments are being eroded from all that area, and they're deposited around the lake. So it's a very big area. And just for the geological context, it's along the East African drift system. And that is really very important in terms of understanding a lot of things concerning the context of human evolution. Because it's you have to try and filter out the effect of climate versus what is happening regionally. Because as I will be describing, the sediments and the lake, the river and the lake that have been present in the Turkana Basin for the last 4 million years, when hominids were evolving, early humans were evolving, has a lot to do with tectonics. whether there is a lake or not. Actually, that was part of my PhD dissertation. So you first of all have to filter that the effect of tectonics in order for you to try and understand the effect of climate on the evolution of hominids and other mammals. And on the left there is the various stages of faulting, rifting that has been taking place. And you can see it dates back all the way to Cretaceous. And you have some Miocene and now the present, which is mostly blue. So that is a very important context to understand, and I'll be talking about it later during the presentation. And the arrows are showing you the extension rate of the rift system. So it's extending almost at the rate at which your nail grows annually. So that doesn't seem a lot, but it's very, very, very fast. So and that has a lot of implication as far as the geology is concerned there. So the frontiers in petrology. So petrology, most of the work that I've been doing interfaces with other fields. Traditionally, petrology has been used a lot in the context of chemistry, which is mineralogy. So people use petrology, they do a lot of XRD. So that has been the main application of petrology, and lithology, something that has to do with composition. The construction industry also uses petrology a lot. Concrete, they make thin section. Even the first internship that I had as a petrology student was in a geomechanics lab that was doing engineering. So there's a lot of aspects that petrology helps with there, and also paleontology, so the biological aspect of science. But that is where most of the sedimentary petrology fits in, because you have to consider the influence of living organisms, the effect of organic material. So that's make sedimentary petrology very important, especially when you include mudstones and shales, because biological living organism, bacteria, have a lot of control on the type of mineral that will precipitate, and even their characteristics, their shape, their sizes, and that has a lot of impact on many things. So starting with my studies concerning oil and gas reservoir, when I was hired by Schlumberger in 2006, for the first 5 years, I had an opportunity to study more than 100,000 samples, petrology samples. And the industry has, one of the advantages they have is because they have the technology and they have a lot of samples from all over. So I was fortunate to be able to look at those samples and try to see how they relate, how they can help us understand, the geochemistry of reservoirs, petrophysics, geomechanics, and even basin models. And one of the things that people, it's almost like a paradox. When you tell people that you can take something that is really tiny, sometimes petrology samples are almost as small as the tip of a pen. You put them in SEM, and to be able to tell somebody that you can look at that sample and be able to tell them about reservoir, it's very difficult for a lot of people to understand. But it's easy for them to understand that if you look at somebody's DNA, you can be able to tell a lot about their ethnicity, about diseases and many other things. So it's the same concept, even though the petrology part is very old. So from this study, I was able to demonstrate that petrology can have that kind of application all the way from microscopic features up to basin scale models. So some of the examples that I'm going to show you here illustrate that. So to begin with, so these are these sections here that are shown on top. And you see a combination of minerals and organic material. So the biological component and the mineralogical component. So just by looking at those thin sections, the type of organic materials you have there, the type of fossils, you can be able to understand which part of the basin that sample is coming from. And those samples are they are quite they're tiny. So, and this is one of the examples that petrology can be almost like molecular biology when it comes to geological sciences. And then you can see how from left to right, the transition in the type of organic material, mostly algae and spores and other things, how they're shifting, the nature shift as you go towards the deeper part of the basin. So, and this is an illustration that you can be able to use petrology to understand the deposition environment, just looking at this section, isolated this section, and be able to predict what kind of trend that you're going to see as you move along the well. Okay, and when you look at that in detail, you can see that it's the mineral that precipitate in association with the organic material. We find that they are very, very, very closely tied with the type of organic material that you have there. So for example, in this case, a lot of fungus or funginite, they tend to precipitate this kind of material, kaolinite, and then you'll see silica. And then you will see some other type of organic material. They precipitate chlorides, clay minerals, elite. Okay. And then you'll have others that will precipitate pyrite and calcite. Okay, so they have a lot of control in the type of mineral that will precipitate, and also their size and texture. Okay, so and you can also do the opposite. So if you see certain type of diagenetic material, you can be able to predict what type of. If you see specific type of diagenetic minerals like pyrite from point of pyrite, you can be able to predict what type of organic material was associated with that. And that is important for people who are studying the reservoir quality, the kind of gas and petroleum that is going to be produced from there. So it's a very, very close relationship between minerals and living organisms. And then, but there is also external factors that determines. This is an example here on top. It has a foraminifera, which are primarily composed of calcite. But as they undergo diagenesis, they can either be silicified or they can be dolomitized. And that will have a lot to do with the chemistry of the water, the temperature, but also with the type of organic material that is associated with that. Because organic material can buffer pH. They can buffer pH and take it so high so that there's going to be a limited type of minerals that are going to precipitate at a high pH. So even though that's a local effect, but if you consider the vast distribution of organic material, then you can start to understand how they're going to influence that. So by understanding what kind of minerals will precipitate at what type of temperature and chemistry and association with organic material, then you can start using actually petrology as a form of geothermometer. Okay. And you can even study the chronology, how the events were taking after deposition, the transformation in terms of time. Okay, so that's why petrology becomes really important because these are features that you will not be able to see on outcrop, but you can see them on very, very small samples, whether they are cuttings or core. Okay, and during the study, I was also able to link the fishes that they map, petrophysical fishes that are based on logs, and assign them to specific type of composition or mineralogy and texture. So those two are very important. So it doesn't necessarily matter how much the total amount of quartz that you have or the total amount of calcite that you have. The texture of that mineral also matters in terms of the behavior of that rock. And that's why you see there's some minerals there that are almost equivalent, but their behavior is different because the texture is different. Okay. So, and that means that you can start also be able to predict the kind of composition that you will see and the texture and the mechanical behavior by calibrating your logs using petrology. And then you can link that to seismic data, and that will help you understand the larger part of the basin. So that is the beauty and the power of petrology. So about 10 years later, I decided to quit the oil and gas industry so that I can have enough time to dedicate to the study of human evolution, because that's actually what my passion was. And the game plan from my advisor, Frank Brown, was the best place to learn, cutting edge petrology would be in the industry, because they have the money, they have the technology, and they have the need for that. So and that's why I went to the industry. And when I realized that I have enough knowledge with me, then it was time to start applying it to the study of human evolution. And so when I left, I set up just a small consulting company so that I can just be making money, but also I have a lot of time to do my studies. So one of the methods that I developed was to be able to use cuttings to study the mechanical behavior of rocks for wells that don't have core. So, and this is an example of what I came up with, that if you look at micro-CT and look at the internal texture of the rock, you will see certain kind of behaviors. They will either fracture as you move to the bottom left there. They'll either have a lot of fractures, or they will have deformation instead of fractures. Okay, and that's what I'm calling here shear deformation ratio. So if you plot that against the number of fractures, that has a lot of correlation with the composition of that rock. Okay, the more mature the clays are, the less fracturing it will have, and the more deformation it will have. And the more mature the clays are, the more fracturing you will have. And it looks like a very simple concept, but it had a very, very fundamental application in terms of understanding the reservoir behavior. And this is an example of the application that I did with some of my colleagues from Gdańsk University. If you look at the composition of these two samples, sample A and sample B, they seem to have identical composition. And that's one of the biggest mistakes that a lot of people do. They take samples and they do XRD, and they try to correlate that composition with strength or with fracturability or with other things, without considering the other aspect, which is texture. So here you see they have the same composition, but when you do nano indentation, then you see the hardness and the Young modulus, they're very different for the two samples. So the method that I told you that I came up with, initially I wrote a patent, but then I decided I wouldn't go that route, because most of the knowledge that I got to develop this method came from Frank Brown. So I decided I'm just going to let everybody be able to use it. So you can see, if you just take cuttings and plot them, make observation and plot them there, they plot differently, okay, regardless of their composition. So what does that mean? It means that if you have a lateral well that is several thousand feet, okay, tens of thousands of feet, and you don't have core there, if you are able to assign the cutting to a depth, you can be able to start having some relative understanding of what the hardness and the Young modulus are, because those features determine how easy it is to fracture or to the mechanical behavior of the well. So that was very, very important. And if it was not petrology, it would have been difficult to come up with that. So let's shift to the human origins. So taking this knowledge back to use it on human origins. So what time do we have? Are we doing okay?
Yes.
Okay, good. So my involvement in the study of human origins started before I joined the University of Utah, and it was from the invitation of Richard Leakey and Maeve Leakey. And this is an image. The top one here is Maeve Leakey excavating a fossil that was found in 1999. So, and that was the year that my undergraduate student, I became an undergraduate student here under Frank Brown. And it was for them to have me involved in this research and my name to appear there, and I was still an undergraduate, and then for them to allow me to draw stratigraphic section, that had a very, very big impact. as far as the science in me is concerned. And that's why even after going to oil and gas industry, making a lot of money, which I did, my heart was still in the human evolution because I saw a lot of value there. And that's why I find it very important to involve undergraduate students, even in research that you think is, it's very, very high level, because that has a very impact in them as far as developing passion is concerned. So that was Kenyanthropus. And then I was also involved in several other research. This was during my undergraduate, my graduate studies in 2007, and we continued doing a lot of work with Frank Brown, and that's an example of we did in 2013, showing the distribution of hominids in terms of time throughout in East Africa. East Africa tends to be an area where we have a lot of hominid fossils. Okay. We have, for example, in the area where Kenyanthropus was discovered, that's where we have the oldest stone tools. They were discovered there around 2011 by Sonia Hammer. And they about 3.3 million years. So, and that's around the time interval where you have Kenyanthropus living around there. We have some of the oldest anatomically modern human beings there in the same region. Chad Fuller worked in one of the sites where those hominids were discovered. Okay, so petrology again. So it's very important when you find for hominid fossil, their value and their significance has a lot to do with the geological context, what age they are, and what kind of environments you can be able to infer. Okay. Sometimes they may be reworked and transferred and redeposited in a different environment. You need geology to be able to know the original context as far as the deposition environments are concerned. So one of the most important work in the Turkana Basin in order to set the stratigraphy was done by Frank Brown. Here he is as an undergraduate student. At that time, he was still at Berkeley. So he developed this method of using volcanic ashes, being able to isolate crystals that are coming from the volcanic ashes and doing dating, isotopic dating on them. And then taking the pumices and associating the glass that is associated with the pumices with the ash, the volcanic ash, okay? And then doing a geochemical fingerprint, and then using that for stratigraphy of the basin. And on the left there is a column showing you the frequency of the volcanic ashes from the last 4 million years up to present. So that was done by Frank Brown, and it looks very obvious until you learn what was happening in the basin before he started doing this. Before he started doing this, they were doing bulk analysis of the volcanic ashes. And they had identified like 3 or 4 volcanic ashes out of these 300 and something. So the stratigraphy was all over mixed up, okay? And for him to be able to be able to isolate various volcanic ashes, he was using petrology to be able to isolate contaminants, because when a volcanic eruption happens and the sediments are being brought by a river, they'll be eroding all the sediment, they'll be eroding some other volcanic ashes, they'll be eroding everything all over. So if you're not able to isolate them and be able to clean them up using petrology, then you will be getting an average that is meaningless, okay? So he used a lot of petrology techniques, and that's where my passion for petrology developed, by seeing how powerful this technique was. Okay, and the other application for petrology again was when I was I think I was an undergraduate student. So I went to the field with him in Turkana Basin, and this is a picture of columnar basalt. Okay, and at the bottom there is some lake sediments. And if you go around the corner, you will see another basalt that is below the lake sediment. And for very many years, when they did the geology, the geochronology of the basalts, they used to show different compositions. Okay, and they had different ages that ranged all the way from almost 3.5 million years, and some even 9 million years. Okay, so they say they have to be different. And here you would actually say, they're different. There's one at the bottom and there's another one at the top. Until one day, when I was there in the field with Frank, and he sent me to one of the outcrops, and he wanted me to look to see the shell beds forming a biome on top of a basalt. Okay. But when I went there, that's not what I saw. I saw this contact between the basalt and the sediment, and it looked like something that I've been seeing at home when I was a kid with the cooking. When using firewood, you have three huge boulders, rocks, and then you put a pot on top. And sometimes the pot will spill over, and then the water will be on a very hot rock. If it cracks, you can see the edges of that rock. It has some kind of obsidian, so it's a chilled surface. And that's what I saw here. And I said, it looks like something was burning. And that observation was important for us to be able to figure out the stratigraphic, the geochronology of these basalts. And when we looked at, we spent about 3 or 4 years going to all the sites where these basalts outcrop. And we started looking at the petrology of the basalts. We isolated the diagenetic minerals. And then we noticed that the mineralogy is actually identical. And the fabric is also identical. So texture and composition, those are identical. And we noticed that if you walk around at some point, you will actually see the basalt forming a dike that would come and flow over. So this is actually the same basalt, but in some places just forming dike and coming on top. And that was very important because we realized all of a sudden that this is actually the same basalt. Okay? And the mistake that people are making is by doing bulk analysis and including the genetic minerals, that will set off your chemical composition. Okay? So you're doing averaging, which is not the best way to do it. So, and this was, to me, it was the best example of physical stratigraphic dating. And we were able to identify that actually this basalt is associated with the lake. It was during the extension of the basin, and the subsidence and the lake formed, and the basalt came through. So the basalt has to be almost the same age as the rock, as the lake. So from that, then we were able to use the seismic data and map the distribution of the basalt. They used to call it orange reflector. So we were able to map the distribution of those basalts all over. And also we use the same kind of understanding to map some other basalts, which are shown here in orange. Okay. And that is very important because it showed us the sequence of basalt volcanism in association with faulting and time intervals where lakes were forming at the same time interval, the basalts were erupting. Okay. So, for that reason, we were able to understand the evolution of the basin and to be able to note to people who do paleoclimate, not to use lacustrine sediment or fluvial sediment as an indicator of either increasing precipitation or drying up, because that has a lot to do with tectonics, okay? So, and by doing that, then we were also able to know the depth of the various stratigraphic units. And even though most of them don't form outcrop, you can be able to predict if you want to find a new outcrop where you want to go, because you'll go somewhere where you have faults that have been active at a certain time interval, and you want to go where adjacent to some of those sediments that you want to identify. And that's the technique that Frank Brown used for very many years to map and identify new outcrops in the basin. Okay, so when I worked in the industry, we were using logs and calibrating them with Petrology. Okay, and we will draw a profile like this. It will be a continuous prediction of what kind of lithology you expect to find based on isolated samples. Okay, so I said, why can't we use the same technique? Instead of logs, we use satellite data. Okay, and this is an example of the application of satellite data to try and look at the outcrop petrology and calibrate it with satellite data. And that way we could be able to map sediments that had specific characteristics and probably be able to go there and see whether we can find a fossiliferous outcrop, because we could be able to isolate the signature of fossiliferous outcrop by knowing, calibrating it with the site where we know we have fossils. It didn't work very well because of the resolution of the satellite data. So the next phase, actually, which is funded by Sony Group, is to try and use the drone so that we can refine the resolution. And Chad, who was also a student of Frank Brown, and he has worked in the Basin, he's a drone pilot. That's what we are trying to see whether we can use improve that resolution and be able to apply the same technique. And if we are able to do that, it will help a lot in terms of increasing the potential area of where people should be looking for fossils. Because I remember that's one of the things that Frank told me. The most important work that a geologist should do is that they should be leading. They should be expanding outside the area and finding new outcrop where people can be able to look for fossils. So that is the motivation behind that. So that's one of the projects that I'm working on, to be able to use a drone and outcrop petrology to look for new outcrops. And the other application of petrology is for provenance of fossils. We find a lot of fossils on the surface. And this is an example of one of the studies that Frank Brown was doing. He was not, and he passed away before he was able to finish this project. And I took over and I was able to finish it. And those teeth, they came from outcrops here. The excavation areas, they almost like the size, almost the size of this building. So they're isolated, they didn't come from the same place. And they don't seem to come from the same horizon. But if you put them together, it's one individual. So definitely there's something happened with the reworking or something like that. Okay, and that's one of the biggest challenges that we face when you don't know. You find fossils on the surface, and you can't be able to relate them to sediments. And sometimes you don't know what has been reworked and what died there. So, and this is an example of teeth from the same hominid at the top there. And if you look at it, it has microfractures that are filled with barite. And when I saw that, it reminded me of the cuttings that I work with in the oil and gas. It's almost the size of cuttings. We find a lot of barite in cuttings, and we use it for provenancing the fossil to a specific horizon. Because before the barite came and filled these structures, it must have come through the sediments. So you'll find traces of barite, of the same minerals, in other parts of the sediments. And if you use the petrology techniques, the barite that is from the same time interval, it will have identical crystal structure. Okay, and it will have identical trace components because no mineral is completely pure. So if you look at the trace components and the crystal structure, then you can be able to correlate that barite, which is from the tip, and a similar mineral that could be from the outcrop. And it doesn't even have to be from the outcrop, because barite means at some point in time during preservation of this fossil, there was some kind of hydrothermal fluids going through, because that's the only way you will be able to transport that kind of mineral. So we are doing a study. We are planning to do a study through Stony Brook University to be able to do this kind of thing. Because we can't be able to make a dissection from a hominid tip. So we have to use some kind of imaging techniques, micro CT and other techniques for us to be able to look through that. So this will help us to be able to provenance fossil very, very specifically to the environment which they came from. And these are examples of various types of fossilization, the same tree. So it's organic material. But depending on the environment where it fossilized, it could either be fossilized, it could be silica, or it could be even calcite. Okay, so that means that all the outcrops where fossils occur, they have their genetic signature associated with that. And that is what determines the kind of fossilization that you'll have. So if any of those fossils was eroded and transported elsewhere, you can be able to link it back to the fishes that it came from by looking at the sediments, because they have to be at equilibrium in terms of preservation. Okay, so that's another example of application in petrology. So, and as far as conclusion is concerned, one of the things that I would be able to recommend, especially to students, undergraduate students, and even graduate students, is there's a lot of opportunity in petrology. We are at a time that I call a renaissance, a new renaissance for petrology, and especially for unconventional reservoirs. They are in very much need of petrology, because when they're doing mudstones are very, very difficult to characterize, because you find, like, clay minerals, they're almost 10 or 15 different kind of minerals in there. So, and that's where the application of petrology has been. And I know that there are a lot of places now that are producing a lot of these sections, and they're not enough petrology to be able to look at those things sections. So they just end up scanning them and putting them in storage somewhere. And that knowledge, as I demonstrated here, is transferable. You can use that knowledge if you want to go back and do paleontology or carbon sequestration, any other thing. It's transferable knowledge, okay? And then the synergy between academic and the industry, okay? So I don't see a lot of that synergy going on. And most of the industry, a lot of research that they do, could be, there's a lot of confidentiality involved in that, and they don't publish a lot, but they're still in need with people who can be able to do research, and especially in the energy, in terms of unconventional reservoirs, and also renewable resources, and also the construction industry. As I told you, I used to be in charge of petrology, so I was helping with procurement of a lot of petrology equipment. And one of the things that I learned is the biggest consumer of thin section equipment is the construction industry, because they make thin section out of concrete. Okay, so there's a lot of opportunity available for petrology in a lot of things. But for you to be able to take advantage of that, it will be good to be able to put a lot of emphasis on mudstone petrology. Okay, sedimentary petrology, and put a lot of emphasis on mudstones. Because the foundation of buildings and all that material, that most of them have a component of clay minerals. And then have a lot of microscope skills. In addition to photographic microscope, SEM, most of this image I took it from the physics department. So there are a lot of equipment here, microscopes, that can be used for petrology. And then have a very good understanding of include organic material in your studies. Don't just concentrate on minerals. Also look at what is happening with the living organism, because they also have they also mineralize, and they control mineralization. Okay, so that's the end of my presentation.
Plenty of time for questions.